Hello everyone, I'm Jihyeong from KAIST. Today, I want to share our research about unsupervised episode generation method designed to enable unsupervised graph meta-learning. Ordinary few-shot learning was emerged to allow machines be able to learn from only a few labeled samples to classify unseen classes like humans. For instance, humans are able to classify this image as a pangolin's image, but the deep neural networks require more and more label samples of pangolin or armadillo to classify this image as pangolin. To solve aforementioned few-shot learning tasks, episodic learning was widely employed, especially in meta-learning. Instead of commonly used mini-batches, episodic learning uses a bundle of episodes that mimicking the format of the downstream task to train the model. Hence, episodic learning allows the model to also learn about what task to be solved in the testing phase. To understand our task few-shot node classification and graph structure data, let us know about the ordinary node classification task first. Ordinary node classification task requires a model to classify unlabeled nodes into one of the known classes. However, in few-shot node classification task, the model have to predict unlabeled nodes into one of the unseen classes during training. To solve this task, recent researchers tried to develop a graph meta-learning based methods, or just applied graph contrastive learning with fine-tuned linear classifier. Although supervised graph meta-learning methods are effective, their label scarcity problem has to be resolved. This is because the amount of available label data determines the amount of nodes that they can utilize for training, which is crucial in few-shot node classification. While GCL methods are not affected by the label scarcity problem, inherent class imbalance in the graph deteriorates their few-shot node classification performance. As they cannot attain the knowledge about the type of the downstream task to solve, thus they lack generalized abilities for solving few-shot node classification task. In a nutshell, we have reached to the solution unsupervised graph meta-learning. By enabling the unsupervised graph meta-learning, all the aforementioned issues can be resolved. We can use all nodes in the graph, while we can also make model to learn about downstream task format information. To do so, we propose unsupervised episode generation method here. When you look at each component in the episode, we found that all the related works like UMTRA and AAL, or even ordinary supervised methods, require that queries should have similar semantics with the support set. Thus, we decide to utilize similar nodes as queries to make training episodes without labels. To discover similar nodes to use them as queries, we use raw node feature similarities or structural similarities by graph diffusion. This is the methodology overview. After calculating similarities between nodes, we randomly sample sets of n nodes and assign distinct pseudo-label for each of them to generate the support set. To make query sets, we find similar nodes of each support set nodes with pre-calculated similarity matrix. And this is the overview of our methodology variant NAQ diffusion. Unlike aforementioned NAQ feature, it uses structural level similarity calculated by graph diffusion, while other processes for episode generations are same. As you can see until now, simpleness is one of the advantages of NAQ. The other advantage of NAQ is its model agnostic property. Since NAQ make training episodes in the same common format of ordinary supervised episode generation, NAQ can train any of existing graph meta-learning methods without using labels. This is our experimental results. Across all datasets and all settings, NAQ can outperform all of the other baselines. In addition, NAQ is really model agnostic. It can retain or even improve the performance of existing graph meta-learning methods without using labels. Lastly, by unsupervised graph meta-learning with NAQ, we can improve the tail class embedding quality, which proves our superiority over GCL baselines. Thank you for watching the video. If you are interested in our research, you can access to our paper or source code and full version slides by QR code above.